Good morning. In this lesson, we are going to focus on graphing polynomial functions. The way you can expect this lesson to go is I'm going to start with giving you 5 steps for graphing polynomials. We've covered a lot of material in the last few lessons, and these steps are just going to guide you into which pieces of information you need and how you put that information together in a logical way. Then I'm going to work through 5 example problems, which I know probably sounds like a lot, but there's a lot of different twists and turns that you can see in these problems, and I don't want you to start wrestling with those twists and turns when you're on your own. Then next class, I'm going to give you several problems to work on your own to sketch those graphs, and you will have the entire class period to do those. So I'm going to start with these general steps. The first step when you're graphing polynomials is to determine the end behavior. And we've gone over that. That is a skill that we have studied independent of trying to graph, just figuring out which way is the end point. So to figure that out, you do need your degree and the leading coefficient. So if you think back to some of the first lessons we did coming back from the break, we focused on that vocabulary, like what is the degree, what is the leading coefficient, and then in the next class we did, okay, what do we do with that? We can determine the end behavior. So now we're going to draw on that skill to figure out which directions the end points. Now, the second step is one of those steps that you might need to do or you might not need to do depending on how the problem is given to you. So you need to factor your polynomial to find the roots. And if you think back to our lessons on factors and roots, we needed those polynomials in factored form. When they're in factored form, they're really, really simple to get the roots from. It's when they're not in factored form. So I'll put a little asterisk next to this because we don't always need to factor them. Sometimes the polynomials are given to us factored. And what happened last year when I gave the test on this was that I gave students some polynomials that were in factored form. So they were really, really simple to graph, and students missed doing it. They just thought, oh, this is a hard problem, so I'm not going to do it. And they missed out on some pretty easy points because they were thinking that they had to do more than they needed to do. The third step is to plot the roots. And by that, I just mean you put a dot wherever the root is. Remember that the root is the x-intercept. So it's an actual point on the graph. It is the point where the graph crosses the x-axis. So once you know where the roots are, you're going to put a dot where every root is. Then you will sketch the ends, and that's going to take you back to this step right there where you determine the end behavior. So you're going to put the roots in, then you're going to put the ends in, and then lastly, we are going to add in the rest of the graph. Now, there's a lot more that you could do with polynomials. You can figure out where the turning points are. You can figure out if there are turning points that are like in between x-intercepts and stuff. There's a lot of stuff. We could study polynomials for a very, very long time. But we're going to look at the main concepts, and we're going to get a handle on how to graph some fairly simple polynomial functions. So now I'm going to work through the 6 example problems that we have. 5, I'm not doing an extra one. I mean, 5 is more than enough already. So 5 example problems. And as I'm doing that, you should be writing it down. You should be following along with the steps. If at some point I move a little bit too fast, you know that this video is posted on YouTube. You can go back and watch the video again and pause it and back it up as much as you need. As much as you need to. All right, so let's go ahead and take a look at the first example. Now, I wish there was a way on the program that I'm using that I could put my coordinate grid like over here So if you're following along on the notes that have been uploaded to Teams, you'll notice that I have like the work done on one side and then I have the sketch of the graph like over here. But the only way I can do this is to put like the background. I can do the coordinate grid background and it's smack dab in the middle of the screen, which is not exactly where I want it, but you know, we work with what we got. So, okay, let's go back. Now, the way that you should be doing this is you should have the example problems, but you should also have those 5 steps written down. And you go back and you look at the 5 steps. And the goal is that as you see more problems, as you do more problems, you don't have to look back as much. So the first step says determine the end behavior. We need the degree and the leading coefficient. So my degree for this polynomial is the highest exponent, which in this case is a 3. And the leading coefficient is a 1. Okay, so I'll kind of put that in there. If you don't see that leading coefficient, it is a 1. And this tells me my end behavior. So this tells me that it's like a line, and the positive leading coefficient tells me that it's a line that tilts upward. So my end behavior is left, down, right, up. That is my end behavior. Several of you on your homework were stating your end behavior in a way that I did not teach you to do it. You were saying stuff like falls to the left, rises to the right. Now, of course, I know what that means. I also know that that is a phrasing or verbiage that's used in other textbooks or other online resources. So it's totally okay to use other resources as long as you fully understand what they are saying. I think it's actually harder to say that than the way I told you to say it, like just left, down, right, up is easier than saying it falls to the left and rises to the right. But that's your call as long as you understand it. That's the important part. Okay, let's go ahead and take a look at that second step. Second step is factor to find the roots. So this clearly is not factored. And so we need to draw on our factoring skills. This is a polynomial with 4 terms. And if you recall from the last lesson, we want to engage factoring by grouping when we are dealing with a polynomial with 4 terms. So bring down the y squared. And in this first group, I'm going to factor out an x squared. If I have x to the third and I factor out an x squared, I'm left with x. If I have 3x squared and I factor out the x squared, I'm left with 3. And then over here, remember we're aiming for another x plus 3 over here, if this is going to work at all, which it will. We want the other x plus 3, and we can see that would factor out a -4 in order to get that. If you want to do a quick little check, you do -4 times x would give you -4x, and -4 times positive 3 would give you -12. Now we have a common factor of x plus 3, so I'm going to go ahead and factor out the x plus 3. And that will leave me with x squared minus 4, which I recognize is the difference of 2 squares. So we have x plus 3, and then the x minus 4 factors into conjugates, x plus 2 and x minus 2. This is enough for me to get the roots. So if I have a factor of x plus 3, then I have a root of x equals -3. If I have a factor of x plus 2, I have a factor of x equals -2, and a factor of x minus 2 gives me a factor of 2. I know from a few lessons ago that if a root appears just once, then it will cross. And so this particular polynomial is going to cross at -3, -2, and 2. Now, I'll pause here because I know some of you are probably busy writing that down. Notice how the skills that we've covered, they're building on each other. So once upon a time, I spent an entire lesson on how to factor the difference of squares. But by the time we get to this point, it is assumed that you know the difference of 2 squares and you are able to factor it. At least when I do it, you're able to recognize it. I spent an entire lesson on factoring by grouping, and so I don't slow down so much to explain every single step at this point. It's why it's so important that you keep up with your math work on a daily basis. And you're not trying to pile it on, because then it becomes just too much information. It has nothing to do with whether you're smart or not. It has to do with trying to absorb too much information at once. So you really need to make sure you're staying up to date with that. All right, next step in the purple there is plot the roots. So I have a root here at -3, a root at -2, and a root at 2. And I know that whatever this graph is, it's crossing the x-axis at those points. Remember the zeros, the roots, those are actual physical points where it crosses the x-axis. Next step in step 4, which is the blue one, is sketch the ends. And so now I'm going to go back to this. The left points down and the right points up. So I'm going to go to my left-hand root and draw it going down, and the right-hand root and draw it going up. Ta-da! Put your ends in. And then the last part is sketch the rest of the graph. So here's what we know. You follow along, put your pencil, Follow along, put your pencil down, just kind of watch what I'm going to do on the screen here. I know that the graph going from left to right crosses the x-axis, then somewhere up here it has to turn around because it has to cross again right here. Turn around, cross here, and then it's got to turn around again so it can cross over there. So what I'm going to do in my green is just try to fill that in. It's not perfect. It's not perfect by a long shot. This is what's called a sketch. It's not this super precise thing. Now, in a more detailed class, if we were going to really study this in detail, we would actually figure out where those turnaround points were so that we could get a really accurate graph there. But that takes a lot more time, like more time than it's worth to actually try to figure it out. This will get you a pretty good graph of what that looks like. Okay, let's go on and look at the second example. They'll go a little bit faster from this point out. So here's our next example. This one is f of x equals x to the third plus 4x squared minus 16x minus 64. Step number 1, determine the end behavior. For that, we need the degree and the leading coefficient. So we know that the degree of this polynomial is 3. That's odd, which means it's like a line. It's odd. And the leading coefficient is 1, which means it's got positive slopes. So we're dealing with left, down, and right, up. So that's our first step, is to figure out what is this function doing at the ends. Step number 2, factor to find the roots, if that is needed, which it clearly is because this function is in standard form. As with the one before, we've got 4 terms here, so we're going to engage factoring by grouping. Looking at the first group, we have x to the third plus 4x squared. I have a common factor of x squared. And when I factor that out, x cubed, factor out an x squared, you're left with an x. And then I have 4x squared, factor out the x squared, I'm left with a 4. Remember, when we get the other group, we should be getting an x plus 4 out there. And you might be able to figure it out from here. You're actually going to factor out a negative 16. You can do a quick little check on that. Negative 16 times x gives you negative 16x, and negative 16 times positive 4 gives you negative 64. Factoring out the x plus 4 leaves us with x squared minus 16, which of course is the difference of squares again. So I would have x plus 4, and then this, the difference of squares, factors into conjugates, x plus 4 and x minus 4. Sorry. To determine the roots, we use what we know about factors and roots. So we have x equals negative 4 and x equals positive 4. And we know that if a factor or root appears twice, that it will bounce off the x-axis, and if it appears once, that it will cross the x-axis. So that's the little twist. That's what makes example 1 a little bit different from example 2, so you can get an idea of when you might see that. Step number 3, plot the roots. So I'm going to use my purple here, and I've got a root over here at negative 4, and I have a root 2, 3, 4 over here at positive 4. Step number 3, sketch the ends. Once you're done with the factoring, it actually goes really, really fast. So sketch the ends. So we go back to our end behavior here. The left points down, the right points up. I'm going to go ahead and put that in. Left points down, right points up. And my last step is sketch the rest of the graph. Now here, I know that it bounces. So the graph, again, like put your pencil down and get your eyes on the screen so you can see what I'm tracing up here. We're moving from left to right. I know that it bounces off the x-axis, so it's not going to cross it. It's actually going to bounce and turn around, and then it's going to have to turn around again in order to make it over to this 0. So when I go to fill in the graph, it looks something like that, where you have it bouncing at one spot and then crossing over on the other spot. Now the goal with this is that as I keep going back and looking at that list of steps, that I don't have to keep looking back. I repeat it enough so that it begins to stick in my head. And what you should have by the end of this lesson is not just those general steps, but you should have 5 really solid example problems that if you forget what one of the steps means, at least these, I'm color coding it so you can see, match the color of the step with the color that I'm using on the graph here, so you can see exactly what each step should look like when you carry it out. All right, moving on to example 3. So this one is a little bit different. This one is also a cubic, and but it doesn't have 4 terms to it. So this is not a good candidate for factoring by grouping. So now we have to kick over to our other skills, our other knowledge of what we know about factoring, and hopefully the first thing that is coming to your mind is look for a GCF. And when I look at this, I can see that I do have a common factor of x. I've got x to the third, x squared, and x. And so we'll take out that common factor, and that'll leave us with 2x squared plus 5x minus 3. Now I need to check to see if this is factorable further, and if it is, I need to go ahead and factor it. And oh, I did my steps out of order. Oops. I just realized that because I realized I was writing in the wrong color, and I was like, but I'm not supposed to change my color right away. Well, so much for that. All right, I'm going to switch colors so that I'm using the right color, and I'm going to keep on with the factorings because I don't want to change steps midstream, and it honestly doesn't matter. In order to factor this, we're going to use slide and divide. So I'm going to take that 2 and slide it on down, and I get x squared plus 5x minus 6. I am looking for 2 factors of 6 or negative 6 there that add up to positive 5. You want to be careful there because there's actually a couple things that you could use. You might think, oh, 2 and 3 add up to 5 and they multiply to 6, except you're not going to get the right sign there. If you do positive 2 and positive 3, yes, they'll add up to positive 5, but they'll multiply to positive 6. So what you need there is you need actually the positive 6 and the negative 1. If you add those, you'll get the 5, and if you multiply them, you'll get the negative 6. Don't forget that you are supposed to slide and divide. So this would be x plus 3, and then we'll slide the 2 back over there and get 2x minus 1. Okay, so now we need to figure out what our zeros are. And we know, just kind of reiterating what the zeros are, or the roots or the x-intercepts, they're where the graph is going to cross the x-axis here. We know the y-coordinate of any one of those points is 0, so you would plug in a 0. Now that might help you figure out what to do with this lonely x. If you have something times something times something, and the product is 0, then one of those things had to be 0, which means what you do with that is you've got an x equals 0. It also explains why the sign flips, because to undo adding, you would do subtracting, and that's what causes the 3 to be negative. And then the last one, I would add 1 and divide by 2, so I end up with x is equal to 1/2. Each of those roots appears just once, so it's going to actually cross at all 3 of those points. Let's go ahead and plot those points then, since I've got them. So I've got one of them is at 0, which is the origin. We have one at negative 3, and then we have one at 1/2, which is like right close to the 0 there. In fact, I can't even quite put it in the exact right spot. It's a nice reminder that they are, they don't have to be integers. Now, the next step is supposed to be to draw the end behavior. The problem is that I skipped that step at the beginning. So let's go ahead and find that end behavior. The degree is 3. And in this case, which tells us it's like a line, and the leading coefficient is a 2, which is positive, which means we have the left down and the right up. And you'll notice that all three of the examples we've done so far have been left down, right up. So hopefully Miss Taylor will change that up in a future example. All right, now I know what my end behavior is. So I know the left goes down and the right goes up. And so you go to the left dot and the right dot, and then you fill in the rest of it. So it crosses, and then it's got to cross here, and it's got to turn around really, really fast. I'm not totally sure I'm going to be able to draw that real well, and I can't. I'll try one more time. See if I can. Yeah, that's better. So that one's got like a really, really narrow turnaround there. And we don't really know where it's turning around. If you try to graph these on your graphing calculator, you might find that they turn around in like way, way, way off your screen somewhere. And, you know, I'm trying not to I know I try to be really consistent with my colors and the steps that I use. And obviously you can find the end behavior at any point before you need to graph it. All right, 2 more examples, and then we are calling it quits. So for this one, oh, hang on. There we go. That's better. So for this one, there's like good news and there's bad news. And I think the good news outweighs the bad news. So the good news is that this is already factored. This is what I was alluding to at the beginning of the lesson. When it's given to you in factored form, it is like you don't have to do any of that factoring work. It ends up being a really, really fast problem to do. The bad news is that it's not as obvious what the degree is, because you know the degree is the highest exponent. And you look at this and you're like, oh, the highest exponent is 1, it's degree 1. And yet you should know this is not a line because you have more than one x. So you could multiply it all the way through. So you could do, and we did this before, where you take like 3 and you multiply it through, and then you FOIL it through, or you FOIL it through, and then multiply the 3 through. When you do that, you're going to have an x times an x, which is going to give you x squared, and you're going to have degree 2. Now, quick way to do that is simply count up how many x's you have in the factors. But what you're really doing is like you would multiply it all the way through, and degree 2, and that tells you that this is going to be like a parabola, at least its end behavior is. The leading coefficient in this case, if you were to multiply it all through, you would have that 3 sitting out front. So that means there's no flip to it. So we're going to have left up, right up for our end behavior. Next step would be to factor it, except it's already factored. So that's great. We don't even have to do that nice orange step. Although we should write down what the roots are. So the roots are x equals -4 and x equals 5. And they each appear once, so it crosses at each of those points. Don't make these problems harder than they are. If it's already factored, I would honestly, like on a test, I would start with the ones that are already factored. Now we're going to go plot those. So we have a -4 over here, and 1, 2, 3, 4, 5 over here. My end behavior says the left goes up and the right goes up. So like so. And we know that it crosses at both of them. So pretty much this is just going to cross and turn around and come back. In other words, this one actually is a parabola. If you were to multiply that all out, you'd get a quadratic, and it would be a parabola. All right, one more example. And I apologize, this is a little bit messy for some reason. My iPad was not responding to writing on it. This is f of x equals -4. This is -4 here, and then this is an x. So it's -4, x plus 4, x minus 2, x plus 1. And, okay, so this one is the good news. It's already in factored form. The only tricky thing to get through with this is like, how do you figure out the degree and the leading coefficient? And just don't overthink it. If you were to multiply it all out, you'd have to do a lot of distributions. And at some point, you would do x times x times x, which would give you x to the 3rd power. So it actually is degree 3, which tells you it's going to behave like a line. Definitely not going to be a line, but it's going to behave like a line. And the leading coefficient, you notice there's nothing else in front there, that the leading coefficient ends up being the -4, which means that this time it's tilted down. So this time the left points up and the right points down. Okay. Now, again, the good news is that this is already factored, so we don't have to do any factoring here. We just are going to get x equals -4, x equals 2, and x equals -1, and each of those appears just once, so I know that it crosses. Let's go ahead and plot those. We have a 0 here at -4, a 0 at -1, and a 0 over here at 2. Next step is to put in the ends. So I put in the end behavior. The left is pointing up, the right is pointing down. So I come over here and I do the left up and the right down. And then the last step is you sketch the middle. So I know it crosses, it's got to turn around, cross again, turn around, cross again. And I go and I fill that in. And there's your sketch. So each of those examples, I know that's kind of like an intense lesson, but each of the examples does look at something a little bit different. This one is a third degree polynomial where it's already factored, which definitely makes it nicer. This one here is an even degree polynomial, and it's already factored, so that was actually pretty quick to do. You could also graph that by multiplying it together and like finding the vertex and the y-intercept and stuff, so we actually have some other ways of graphing that. This one shows us, this one actually is more to review like different types of factoring, so just to remind you that the factoring might look like, okay, get a GCF out first. This one hits on the factoring by grouping and the bouncing. And this one, of course, does not have the bounce to it. All right, so you don't have any homework tonight other than rewatch this video if you need to. If you feel like this was kind of an overload of information, then I want you to finish, like just rewatch it. Rewatch the examples. Go ahead, put it on like twice speed so that you're not there all day. And listen to me in like chipmunk voice. And then tomorrow you will have some of these problems to do on your own.